Remember when we talked about the nature of light as electromagnetic radiation, we said that the idea that light travels as waves is really important for determining properties of light because what will be true of waves in general will also be true of light waves. And this is an example that just as sound waves show the Doppler effect, the bunching up or stretching out of waves with motion, light waves do as well. So remember that we have the visible light spectrum, and at the long wavelength end, we call that the red end. And the short wavelength end we call the blue end, even though there really is violet there, we can't see too much of that. So we have the long wavelength red end, the short wavelength blue end. Now, if there is a light source coming towards you, then because of this Doppler effect, the light waves are going to bunch up just the same way sound waves did and shift to shorter wavelengths. The shorter wavelength is the blue end of the spectrum, and so we call that a blue shift. On the other hand, if an object is moving away from you as it's emitting light, the light waves get stretched out, and that means they become closer to the red end of the spectrum, and so we call that a red shift. And the amount of blue shift or red shift, the amount of Doppler shift, is proportional to the speed. So the faster something approaches, the more blue shift you see. The faster it recedes, the more red shift you see.
If a galaxy is moving away, its light is stretched. The interval between wave crests gets longer. The light appears redder. The faster it's moving, the redder the light. If a galaxy is moving closer, the light is compressed and appears bluer.
Now, you don't actually see this red or blue color unless the object is moving very, very fast, and we'll see an example of that later on. But the way you detect this Doppler effect is by looking at the spectral lines in the light using spectroscopy that we studied before. So imagine that this is light coming from, say, a star, and it has particular spectral lines coming from particular elements, and those lines are going to be at very specific wavelengths. This red line, for example, might be the hydrogen alpha line at exactly 656.3 nanometers. Now, what if on a spectrum of that star you notice this? So notice that all these lines are shifted towards the blue end of the spectrum, and they're all shifted by the same amount. So what was 656.3 nanometers might now show up as 652.8 nanometers. So it's become shorter wavelength, and that's because this object is approaching us, and you have a blue shift. On the other hand, if the star is moving away from us, all the waves will be stretched out by the same amount, depending on the speed, and they'll all be shifted over towards the red end of the spectrum. And we call this a red shift, and that tells us that the object is moving away from us. And again, the more shift you observe, the faster this object is moving. Now this is important because it lets us determine what we call radial motion in space. Radial motion is motion towards or away from us. We call it that because if you imagine that the sky is a sphere surrounding the Earth, remember the idea of the celestial sphere, we can measure stars moving this way or that way because we just take a picture of them one day and then take a picture of it a year or two later, and we can measure how much it's moved across our line of sight. But if it's moving towards or away from us, we can't really notice that because the stars are so far away that we don't see them getting bigger as they move towards us or smaller as they move away from us. And so everything seems to sit still in terms of this radial motion, and it's called radial because if we're at the center of the circle, then it's movement along the radius. So we can't actually observe that by seeing how the size of a star changes. But what we can do is we can look at the light. And if we see the light being blue shifted, that means the star is moving towards us radially. If the light is red shifted, then it's moving away from us. And this is, in fact, the way we determined that there are rotating nebulae. We can't see nebulae rotating because they rotate. They're so big and they're so far away that even though they might be rotating fairly quickly, we can't observe that rotation just by watching. But what we do to detect the rotation is that if you were to train your telescope on this edge of the galaxy, and you observed a redshift, which means that all that gas and dust is moving away from you. And then you turn your telescope on the opposite edge of this nebula, and you see that it's blue shifted. That tells you that the gas and dust at this end of the nebula is actually moving towards you. This end is moving away from you, and that tells you that the galaxy is actually rotating, even though you can't see it doing so because it's too slow and too far away. So that's how we know, and we can actually figure out how fast the nebula is rotating by how much redshift there is at one end and how much blue shift there is at the other. So how do we use this to detect exoplanets? Well, this is an image here, an animated image here of a planet, an exoplanet orbiting around a star, and we're observing this from Earth. Now, the gravity from the star is tugging the planet and keeping it in orbit, but the planet itself has gravity. And so it's actually tugging back a little bit on the star as well. And so as this planet orbits this star, it causes a little bit of what we call a stellar wobble. The star goes back and forth. It's tugged in this direction, and then it's tugged in that direction as the planet orbits. I've exaggerated it here just to show you for a little planet. It's not going to cause much of a stellar wobble, but enough that it's going to create a Doppler effect. Because even though we can't see the planet, the star is still wobbling as a result of that orbiting planet that we can't see. And that means that at one point the star is moving towards us and the light will be blue shifted. And then it's moving away from us and the light will be red shifted, and then it's tugged back towards us and we get a blue shift, and tugged back and it's a red shift. And the way we would detect this is that it would be this back and forth Doppler shift that we'd observe in the spectrum. And we can actually tell how long it takes the planet to orbit because of how long it takes for this back and forth Doppler shift to show up in the spectral lines. And then once we know how fast it's orbiting, we can get an idea of the mass of the planet by how much it's tugging on the star. And we can start to figure out the properties of that exoplanet. Even though we've never seen it, we've only detected using spectroscopy the Doppler shift of the parent star caused by the orbiting planet.